So as you heard, my name is Emilio Martinez-Paneda. I'm an associate professor at Imperial College London. And my goal today is to convince you that there's an opportunity now to use computer simulations to predict hydrogen-assisted failures. So I'm going to overview some of our recent efforts in trying to develop a virtual platform that allows us to understand how components and structures behave in the presence of hydrogen. And I think this is an ambition worth pursuing because not only computer modeling can give us complementary insight to that of laboratory experiments, but also running experiments in a computer is cheap and efficient. I don't know if there's anyone here from the automotive industry, but I have a friend who works at Volkswagen, and he tells me that they used to crash hundreds of cars in the design stage, and now they only crash 2 cars. If the outcome of those 2 crash tests coincides with what they see in the computer, then all subsequent crash testing is done via simulations. So my ambition is to bring this success to hydrogen-containing environments. I mean, virtual testing has saved billions to the automotive and aeronautical industries. But of course, as you all know, this is not an easy task. Hydrogen embrittlement happens to be a very complex and highly multidisciplinary phenomenon. But the point that I will try to make today is that the combination of this multiphysics, electro-chemo-mechanics modeling and phase field fracture methods can open new modeling horizons and allows you to explicitly simulate the physical processes that are governing this hydrogen embrittlement phenomenon. And if you can resolve the physics of the problem, then you can be predictive. So I'm going to overview, I would say, the ingredients of our computational framework, and I'm going to do so by going through 3 separate stages, the main 3 stages involving hydrogen embrittlement. So I will first explain how we can, model and quantify the ingress of hydrogen into a metal. I will then move on to describe how we can capture the diffusion of hydrogen and trapping, and then finally I will deal with the fracture process itself. How do cracks nucleate and grow as assisted by hydrogen? So let me start with the first stage, predicting or quantifying the uptake of hydrogen into a metal. And in my opinion, this is an area that has not received the attention that it deserves, because there are dozens, if not hundreds, of hydrogen embrittlement models out there, and they all take as a known input. They all assume that you know already this hydrogen concentration at the surface, what is the uptake of hydrogen in your metal. But very often we don't know what is this number. And of course, model predictions are very sensitive to this key input parameter. There's an environment where we have a decent understanding, or in a scenario where we have a decent understanding. And this is when we have our samples exposed to a hydrogen gas environment for a very long time. Then if we assume steady state conditions, then you can use Siebert's law or the Abel-Nobel equation to estimate what is this lattice hydrogen concentration that you have here at the surface. And I mean, this is well known, you all know this very well, so I won't spend much time here. I think the only 2 things that I want to emphasize here is the first one is that the solubility depends on the hydrostatic stress. This is this blue term that you see here. So if you are taking solubility measurements from the stress-free experiments, you must take into account this exponential term if you really want to be precise in there. And this exponential term can be very large. I mean, you have a hydrostatic stress term inside of an exponent, so you can imagine that it will be significant ahead of cracks and other stress concentrators. So that's quite important. And I mean, it comes naturally from the derivation of the chemical potential, but I noticed in the literature that many seem to have forgotten about it, so I thought it was worth emphasizing. And then the other thing that I want to emphasize is that this is only valid for the steady state conditions. So this is not suitable whenever you want to, for example, model hydrogen-assisted fatigue, or you want to capture the interesting kinetics that may be happening at the surface, like we heard yesterday about the interesting role of gas inhibitors. But assuming you have steady state conditions, this is good and convenient. A much more challenging scenario is that when you have hydrogen uptake from an aqueous electrolyte. And when you look at the modeling literature in this area, what you see is that typically this hydrogen concentration at the surface is chosen rather arbitrarily, kind of a fitting parameter without any consistency or connection to the environment. And I completely understand this because, well, you need to start from somewhere, and predicting the uptake of hydrogen from an aqueous electrolyte is quite a challenging problem. So there's quite a lot of physical elements involved in there. Not only you need to resolve the surface reaction kinetics, which includes now all the hydrogen evolution reaction contributions, but also you need to resolve the electrochemical behavior of the electrolyte, because you need your local pH and overpotential, and that local pH and overpotential inside of a crack is going to be very different from the one that you have in the bulk electrolyte, which is the one that you can easily measure. So there's some challenges in there. And I tried to tackle this first together with Alan Turnbull, and we came up with these generalized boundary conditions for resolving the electrochemistry diffusion interface. And then, as you can see, we were able to define an absorption flux that depends on the absorption and desorption reaction rate constants, and also on the surface coverage. And I think that this was a promising first step, but I was never completely satisfied, because we had to make some assumptions, and particularly we had to, as you can see here, we had to compute this surface coverage based on a number of reaction rates, and some of these reaction rates depend themselves on the local electrochemical conditions, on the local pH and overpotential. And again, so this means that for the model to be accurate, you need to be able to measure those reaction rates in specifically the same environment that you have inside of your crack, and this is going to be a bit of a challenge. So I tried to take this one step further, and this is work together with my postdoc, Tim Hageman, and we tried to develop a complete electrochemo-mechanical model that was able to resolve all the physical processes that are happening in the hydrogen uptake phenomena. And by resolving all the physical processes, then you are able to eliminate all the assumptions from the model. So you need to take care of, as you see here, the kinetics of the hydrogen evolution reaction, the absorption kinetics, but also the electrochemical behavior of the electrolyte. So yeah, essentially these are the reactions that you are concerned with. So the usual Volmer, Heravisky, Tafel, and absorption reactions. And then, of course, each of those reactions have their own forward and backward reaction rates that you also need to incorporate in the model. And at the end, the finite element model looks something like this. So you effectively have three domains. First, you have the electrolyte domain, where you are solving for the electrolyte potential and for as many ionic species as you need. You can see here, as an example, the ones that we took for numerical examples. Then you have, on the right-hand side, the metal. So you have a metal domain that typically will contain a crack or a defect of arbitrary size. And there you're solving for the displacement field and the lattice hydrogen concentration. And then between that electrolyte and the metal, you have essentially an interface where you need to solve for this surface coverage. So I'm going to just briefly describe what are the key equations of the model, highlighting in color what are the degrees of freedom that we solve for in the problem. So regarding the surface kinetics, you need to account for all the surface kinetics, of course, the absorption and absorption reactions, and all the ingredients that come with the hydrogen evolution reaction. Then in the electrolyte, you need to solve the Nernst-Planck equation for all of these ionic species that you may have. You also need to obtain the electrolyte potential, so you need to assume local electroneutrality. And then, of course, we're also interested in estimating the overpotential. And then on the right-hand side, on the metal electrolyte, this is the usual business. You solve for the balance of linear momentum, and then you solve a hydrogen mass balance equation that which can include or not traps. And this is the kind of results that you get. So on the left side, you can see basically the pH distribution within the electrolyte, and you can see how actually the pH changes quite dramatically from the value outside in the bulk towards the numbers that you get inside of the crack. And then on the right-hand side, what you see is the distribution of lattice hydrogen concentration, so you can see how the model can predict in the space what is the lattice hydrogen absorption that you're getting into your problem as a result of that environment. And of course, this was results computed for an applied potential of minus 0.5 volts, but you can change the applied potential, and you can change any condition that you want. So you can also change, you can also plot other relevant quantities, for example, the electrolyte potential. You can also plot the concentration of ionic species, and you can do that for different materials, for different fluid flow velocities. You can do this for different temperatures. So you have a virtual platform that allows you to change the environment and see what is the uptake of hydrogen. So we have exploited that also to build some maps to establish some relationships between the applied potential or the environment and the hydrogen uptake at the crack tip. And this is the kind of behavior that you will see, as you would expect. You have this transition, these three regimes. And we hope that this could be useful for many here, because whenever you're developing a model and you don't want to resolve all this electrochemistry, you can take this as a first order approximation to define your hydrogen concentration at the boundary. And of course, the model, you can interrogate it further, and you can, for example, change the applied potential and see what the reaction rate terms are dominating over certain regimes. And I'll just finish this first part by explaining how we can also take this complete electromechanical framework and particularize it to the case of gaseous environments by being able to resolve the transient problem, so the kinetics of the hydrogen uptake in gaseous environments. And this is quite convenient, because then we can look into fatigue, and we can look into other effects that you cannot do when you take the steady state assumption. And the way to do it is straightforward. You just kill all the electrochemistry terms, and you reduce everything to this Tafel and absorption reaction rates. And we shouldn't probably be calling it Tafel anymore, because it's more a combination reaction constants. But then you have an expression that depends, as you can see there, on the hydrogen pressure, and you're able to predict the uptake of hydrogen also in those gaseous environments. And of course, if you consider very long exposure times, if you particularize the model to steady state conditions, you get this kind of Siebert's law behavior that you would expect. So that takes me to the second part of the model, the stage 2, the hydrogen diffusion and trapping. And I won't be spending much time here because this is a more mature area. What we have done is, like others have done, we have developed multi-trap diffusion models based on both Oriani's equilibrium and on the McNabb-Foster's theory. And I think the only point that I want to emphasize here is that I think it's quite important to take into account the role that G&D's geometrically necessary dislocations play on this trapping behavior. So if you really want to capture what is the dislocation trapping density, you need to account for the role of these geometrically necessary dislocations. And we do that by using this tailored dislocation model, so we can express this total dislocations density as a function of the density of statistically stored dislocations and geometrically necessary dislocations. And this Taylor model allows you to relate these quantities to macroscopic quantities like plastic strains and plastic strain gradients. And this goes back to my work with Rick Gangloff in 2016, but I thought it was a very important point to emphasize because experiments have consistently shown that G&Ds dominate material behavior near crack tips and inclusions. So if you really want to estimate your trap density precisely, or I mean, you have a sensible estimate of trap density, you must account for this. And G&Ds are not only important to estimate precisely the trap density, but also because they act as obstacles to the movement of other dislocations, so they elevate the stresses as we see in indentation and in many other microscale experiments. And you can see here how it comes naturally into play into the definition of a flow stress through the Taylor model. And basically the key point is that when you use this more richer description of what is happening and you simulate the tensile stresses ahead of your crack, what you see is that your tensile stresses become quite large near the crack tip compared to conventional plasticity models that only characterize the behavior of these statistically stored dislocations. And of course, if your hydrostatic stresses are much higher ahead of your crack tip, this means you're going to have much higher hydrogen concentrations. And I think this is important because this provides a modern rationale for hydrogen-enhanced decohesion mechanisms. So the cohesion requires very high stresses and hydrogen concentrations, and this is one source of those stresses. And in fact, when you look at the experiment, this is the only way you can capture, taking into account this G&D effect, is the only way you can capture this elevation of hydrogen concentration that you see as you approach the crack tip, as you can see here. Okay, so that takes me to the third stage of the model. And what I want to show here is how we have used this phase field paradigm to capture the evolution of cracks in this multiphysics environment. So let me introduce briefly this concept that many of you are already familiar with. The idea is very simple, but computationally very compelling. So whenever you have two phases, like crack material points or intact material points, you can describe the interface between the two as either a sharp discontinuous interface, or you can smear their interface over a finite domain and use an auxiliary variable, this phase field variable, to describe where the interface lies. So this phase field will take a distinct value in each of the phases, like 0 in intact material points, 1 in fully cracked material points, and then it will vary smoothly in between. So then you can define a differential equation for the evolution of this phase field, and by solving this differential equation, you're able to capture interfacial problems of arbitrary complexity. And there's multiple advantages to it from a computational perspective. 3 that I like to emphasize is that the interface equation is defined in the entire domain, so there's no need for any special treatment. The second one is that topological changes such as divisions of merging of interfaces can be naturally captured without any ad hoc criteria, so it's very clean. And the last one is that it's very well suited for multiphysics problems because you can couple this interface equation with equations describing other physical phenomena. And in fact, phase field modeling has been a revolution in many areas of science and engineering. It is by far now the most widely used tool to simulate microstructural evolution. It is becoming also very quickly the dominant tool in computational fraction mechanics. And we have recently shown that it can also be used to simulate corrosion, bringing this kind of virtual testing paradigm to the area of corrosion, because you can use the phase field to describe how the corrosion front evolves. But today I'm going to focus on fraction mechanics. You can see it here. So it is, as you can see here, is quite compelling computational tool. You can see that we can capture very complex cracking phenomena. You can see there crack branching, crack merging, coalescence of multiple cracks, nucleation of cracks on secondary sites. So I think it's clear that it's computationally quite robust. And at this point, you may ask, okay, Emilio, yeah, the colors look nice, but does this correspond to reality? Are these predictions physically sound? And I think the answer is yes, because one of the good things of phase field fracture is that it provides a platform for Griffith's energy balance. So predictions are based on the thermodynamics of fracture. And let me just briefly describe this. You know the story. So Griffith postulated that a crack will grow whenever the energy stored in the solid was sufficient to overcome the energy required to create two new surfaces, the critical energy release rate or material toughness. And you can express this, I would say, energy balance or competition between stored energy and fracture energy in a variational form. But solving this problem is challenging because you don't know where your crack lies. And that's where you use the phase field that basically acts as a marker and tells you where your crack is located. And it's a little bit like a damage variable. So it goes from 0 in intact material points to 1 in fully cracked material points, and it reduces the stiffness of the solid, as you can see here on the left. And you can see also that it's a non-local model, which means that results are going to be mesh insensitive. And you can get a good overview by looking at the balance equation. So we have the standard balance of linear momentum with the phase field, the gradient, the load current capacity of the solid. And then you have this evolution equation for the phase field, which is essentially a competition between the critical energy release rate, so the toughness and material property, and the energy stored in the solid, so this is strain energy density, which evolves with mechanical straining. And just by solving this additional differential equation, you're able to capture very complex cracking phenomena. You can see here crack branching as a result of the application of a dynamic load. And this is computed all on the original finite element mesh and without any convergence issues. The method is very robust, and all the results that I'm about to show are computed using standard implicit Backer-Euler methods. So, not surprisingly, the phase field has gotten quite popular in the fracture mechanics community, and I put this slide there to convince you why. So, as you can see, not only can capture very complex cracking phenomena, but it can also deliver a very good agreement with experiments. So my goal here was to try to extend this success to our discipline, to the area of hydrogen embrittlement. And if you want to do so, the simplest model that you can think is, of course, a coupled deformation diffusion fracture model, where you have I'm going to use the simplest equations that I can use for the sake of clarity. And you can see that there are multiple couplings that are happening there, as emphasized with the color. But of course, the critical coupling that we need to think of is how do we couple the hydrogen and this fracture process, this damage process, this evolution of the phase field. And how to do that qualitatively, we all agree. I mean, we know that hydrogen reduces the toughness of metals, so we just need to make our toughness or critical energy release rate dependent on the hydrogen concentration. But the key question is how you do that quantitatively. What is the shape of this hydrogen degradation function that you're going to define? And there's always, of course, the way of doing this in a phenomenological manner. So you can always run experiments at multiple hydrogen concentrations, and then you get a toughness versus hydrogen concentration relationship. But I didn't want to present a model that required a lot of experimental calibration. Ideally, I wanted a model that was able to deliver predictions without any calibration whatsoever. So the good news in that sense is that the model is universal, in that it can accommodate any mechanistic interpretation for hydrogen-assisted fracture. So whenever you believe in the cohesion, in help, or a combination, or vacancies, or whatever, you can always define this hydrogen degradation function as a function of the relevant micromechanical and macromechanical parameters, whatever variable you think that is important. So let me tell you how I define it and what are my beliefs at the moment, but you don't need to agree with me, and you're most welcome to try it in other ways, and people have done that already. So to me, the key question, of course, is how does hydrogen make metal brittle? Like how can we go for these ductile macrovoid cracking fracture mechanisms to this very brittle, often intergranular fracture mechanisms? And if you can explain how you achieve this ductile to brittle shift, then you can have a mechanistic degradation function. And in my opinion, there are 3 ingredients that are needed to understand this ductile to brittle transition. The first one is that if you do atomistic calculations, you will see that you have a very significant reduction in surface energy or fracture energy with increasing hydrogen coverage. So these are DFT results for nickel from Antonio Alvaro, and you can see that you get a 40% reduction if your grain boundaries are completely full of hydrogen. So then the next question is, how much hydrogen do we have in our grain boundaries? And the answer to that comes from Oriani and trapping thermodynamics. So Oriani allows you to plot the trap occupancy as a function of the lattice hydrogen concentration and of the trap binding energy. And you can see that the strong traps like grain boundaries with binding energies of minus 40 kilojoules per mole are effectively full whenever you have lattice hydrogen concentration of roughly 0.1 ppm or so. So it's very energetically favorable for the hydrogen to go and sit in those grain boundaries, as we also seen this morning with atom probe tomography. So those grain boundaries are going to be much weaker. And then when you combine these 2 ingredients with that GND enhanced or gradient enhanced description of crack tip stresses, what you see is that your stresses are typically not large enough to reach the cleavage strength or the grain boundary strength, But the moment you introduce the role of hydrogen, you drop that cleavage strength by 20 to 30%, and then your lines cross, and suddenly you have a story. You have a model that is able to capture this transition from ductile to brittle fracture without any fitting parameters or ad hoc criteria. And the way you incorporate this into phase field is straightforward, because you are solving for a diffusion problem, so you know how much lattice hydrogen you have, where and when. You can relate that through Oriani's equilibrium to the coverage of your most relevant interface, let's say a grain boundary, and then you can go into the atomistic calculations, and then you can connect that surface coverage with a reduction in fracture energy quantitatively. So you only need to run these atomistic calculations once in your lifetime offline. So let me show you some representative examples and of what can we compute with this virtual platform that we have developed. But before I do so, let me just say that we're also interested not only in crack initiation, but also in subcritical crack growth, of course. So we need to be able to capture how, as the crack propagates, as you see in the top, the hydrogen environment, aqueous, electrolyte, or gaseous, follows the crack. So let me go to the results. These are first crack growth resistant curves, R curves. So the y-axis is a measure of applied load, and then the x-axis is the crack extension. And you can see, as you would expect from the experiments, that with increasing hydrogen content, you drop your fracture resistance. Here I'm showing another well-known experimental effect. You know that this is the effect of the loading rate. So if I load very slowly, you can see that there is enough time for the hydrogen to accumulate in the fracture process zone, and then we have a reduction in fracture resistance. But we can also be quantitative. This is a comparison with experiments done on pre-charged steel bars, where we're measuring the notch tensile strength versus the hydrogen content, and you can see that the model does a good job in getting a good agreement with experiments. And these are a bit of more interesting experiments done at SINTEF, where they immerse duplex stainless steel samples subjected to a constant load into a seawater bath environment, and then measure the time to failure. And you can see that the model not only is able to a very good extent, I think, able to reproduce the laboratory data, but you're also very easily able to do virtual experiments over very large time scales, so we can find what is this critical loading below which cracking will not occur. And we have also used this model to gain insight into experiments. So this is work together with a UVA friends, where they suspected that slow strain rate tests were not suitable for measuring hydrogen embrittlement susceptibility due to the initiation of cracks early and at early stages in the testing process. And we confirmed that with our model, so we were able with our model to capture both qualitatively and quantitatively the material fracture and behavior in the absence of hydrogen and for different hydrogen environments, so that gave us confidence in the model. And then we look at the model and saw when cracking initiated, and we observe, as you can see in the slide, that early cracking occurred in SSRT experiments, which compromises the suitability to measure hydrogen embrittlement susceptibility. And effectively, we can model any kind of experiment or boundary value problem. So this is another classic standardized test, STM test, where they're looking at the failure of a screw, high-strength screw that is embedded into concrete. And you can see here that we can basically capture the complete failure of the screw. And more excitingly, we can couple this with inspection data. So this is a 12-kilometer pipeline that was characterized by BP. So as you can see, it has a lot of pit corrosion defects. All those red dots are pit corrosion defects. So we can very easily introduce those defects into our model. We did not model a 12-kilometer pipeline, but we focused on a critical 3-meter section that contained more than 100 of those defects. And then we can subject the pipeline to the in-service conditions. And this is what you see here. I think the video is running. So yeah, you can see that in the top, there are some defects that are starting to merge. Then they eventually coalescence with each other, and then start coalescing with neighboring defects, and eventually you get the complete failure of the pipeline. And this is the images that you'll get if you keep running the simulation. But I think the main takeaway here is that we have a tool that allows us to predict when hydrogen-assisted failures will happen as a function of the service conditions, so loading and environment, and as a function of the material. And the good thing is that the tool is able to do that also at the scales relevant to engineering practice, so levels of complexity and the scales relevant to engineering practice. And we have extended this framework in multiple directions. One direction is fatigue. You can add a fatigue degradation function that to account for the damage, the fatigue and the hydrogen damage. And as you can see, we're able to then compute virtual SN curves and provide a decent agreement with experiments. And we can also obtain as an output of the model, not as an input, the Paris law behavior. So we can obtain the Paris law parameters and the influence of hydrogen on the Paris law parameters. And these are cycle-by-cycle calculations, which means they're a bit time-consuming, but at the same time, they give us much more flexibility. So we can obtain virtual SN curves for arbitrary loading histories, or for example, different geometries. Here you can see an example for a notch geometry. We have also tackled the microstructural nature of the problem. So often you are worried about microstructural effects. So we have, for example, combined phase field with acquisitive zone model to evaluate the competition between intergranular and transgranular cracking. And we have used this, among others, to look at the classic experiments by Zach Harris, Jimmy Burns, Brian Sommerday, where they show that you could get the cohesion in nickel even at cryogenic temperatures, so without the need for any dislocation hydrogen interactions. And we can do that because we can use the model. We see that the model is able to capture quantitatively and qualitatively the ductile behavior that you expect to see at room temperatures, and then we can change the temperature, and we can see that we get, again, good quantitative and qualitative agreement with the experimental observations. And last but not least, we have also combined this electro-chemo-mechanics phase field hydrogen-assisted cracking modeling with that corrosion modeling that I told you before. So we have this phase field paradigm to evaluate the evolution of pitting and stress corrosion cracking and the pit to crack transition. So we can combine this and create a generalized stress corrosion cracking model where we don't need to make any prior assumptions on what is the mechanism that is driving the fracture, either hydrogen embrittlement or anodic dissolution. We can have both in there and just let the model tell us what is going to happen. So we can evaluate stress corrosion cracking failures across a very wide range of applied potentials. And we have also looked into reproducing the Gruel experiments on aluminum alloys, where he was looking into the competition between anodic dissolution and hydrogen embrittlement. And with that, I will conclude with just 3 final concluding remarks. So the first one is that I think that the combination of phase field fracture and this electrochem-mechanics multiphysics modeling is very powerful because it allows us to explicitly resolve those physical processes that are happening in the model. And this is very important because it means that the input to the model are parameters that are physical and that can be independently measured with a dedicated experiment. I think that the second aspect is that I hope that I have convinced you that the model is computationally quite robust, so we are able to capture, it's mechanistic, so we can capture quantitatively what we see in our labs, but it's also computationally quite robust, so it can deliver predictions at the scales relevant to engineering practice. And so this kind of concludes or brings me back to my idea of bringing this virtual testing paradigm to hydrogen-containing environments. And I mean, we heard quite a lot of discussion about whether we can use the gas pipelines to transport hydrogen or not, and this is something that you can easily evaluate with these kind of models in a very efficient and cheap way. And last but not least, I emphasize that the framework is general, is universal, it can accommodate any mechanistic interpretation. I've seen some papers where people are using it for help, for example, and we can easily extend it to account for other mechanisms. I show you microstructure, stress corrosion cracking. We're also doing some work on welding, as you can see there. So you can easily extend it towards your needs. And that's all. I will just finish by saying that all my codes are openly shared. We have mainly used Abacus, but also COMSOL and Phoenix. You can go to our website, and you can reproduce at home all the results that I've showed you today. And I will also, of course, like to thank my funding sponsors, the UK funding agencies, and Tenaris and EPRI. Thank you so much for your patience. Thank you.
So, thanks a lot, Emilio. As it was an impressive overview about what can be done with phase field nowadays.